So thank you for all being here in the session of death, which is very nice of everyone to hang around. I've got lots and lots of slides because we're a project that's produced a lot of output. It's a small group, so I'll hang around and spend more cycles on whatever you want to hear about. I'll move past whatever you don't want to hear about. Feel free to interrupt me at any point. I think the next one is at 5:05? 5:10. Okay, that gives me about 30 minutes. Okay, perfect. I work at Netronome, and I'm here to talk about a new project in the Open Compute project. And so essentially what we're trying to do is get silicon to be developed as a collection of chiplets rather than as monolithic die. And this has taken off in the recent past. What's different about what we're trying to do is trying to make the inter-chiplet interface be an open one so that you can mix and match chiplets from multiple companies. That's the basic aim of the group. And we're going after accelerators. Normally, I have to explain to everybody what an accelerator is and what a domain-specific architecture is. And somehow I feel like this conference, we don't need to go through all that. So fundamentally, we're going after making accelerators. And I tell you why we chose. Then a couple of words from my sponsor, the company that pays my bills. I work at a company called Netronome. The company makes SmartNICs the company makes silicon and then delivers them in the form of SmartNICs. And what is interesting about what the company makes is there's a whole bunch of software it delivers on top of the SmartNICs. Because essentially the aim of the SmartNIC is to offload compute from the host. So whether it's virtual switching, vRouter, or eBPF, or P4, you essentially have a whole lot of ways in which you can program the data path. And all of those need contributions to the the Linux kernel, to OpenStack. And so there's a whole bunch of software that the company builds up on top of that. I'm also here representing the Open Compute project, which, is there anybody here who doesn't know about it? I'll just keep zooming past. Everybody knows about OCP, right? So let's keep going. So everybody knows that there's like 6, 7, a few top-level projects. We are in this, where's the server? I can't even see it. Oh, here, we're in the server horizontal thing, that's us. Okay, so, and then I feel like I can skip past this too. But the more interesting thing about domain-specific architectures basically is that they're still programmable, but that the data path is customized to a domain. So the two running examples I use are Google's TensorFlow, which has a multiply accumulator array for inferencing, and our Netronome's network processor, which has a huge collection of light threads. Because ultimately, if you've built an NPU, the pain point is 40-byte minimum size packets which come along, and you need to somehow figure out how to do 5-tuple or 8-tuple lookup on these miserable 40-byte packets and ship them somewhere. So both of them give you extremely different architectures. Netronome is about how do I do a gazillion light threads. Google's TPU is about how do I move a massive amount of data in to do an inferencing engine. And we'll come back to why. And the main reason you do a domain-specific architecture is for the power performance improvement. So what is interesting about domain-specific architectures is that by definition, they serve a smaller market. And if they're serving a smaller market, and by definition, you're going to domain-specific architectures because you face a compute challenge. And so you want to be on the best, latest, and greatest process node, except that the cost of developing silicon keeps going up on advanced process nodes. So the second interesting thing you can say is I'll take my accelerator and develop it on a more mature process node, in which case it ends up being a bigger die. There's somebody at Hot Chips had this, like the world's biggest wafer or something. Did you see that? It was like, anyway, so the thing is your die becomes too large, and then you start facing yield problems, and you have to break your die down. So either way, DSAs in my mind present an interesting development economics challenge. That's the basic thing that we're here to solve. So the answer, and we've got for those of you who don't know, we've got the whole father of chiplets sitting in the audience here, and he helped me make my last slide, but we're basically rehashing the work he did at Marvell. So, he can interrupt me whenever he'd like. And so basically the whole motivation with chiplets is you've got two broad motivations. One is to take a board and shrink it down because you want lower power, smaller footprint, whatever else. And the other is what we've been discussing, how to disaggregate a die. Those are your two broad motivations. And in either case, you'll benefit from new inter-die connectivity. That's the basic pitch, as a basic motivation for the group. So actually, we've seen all this. We've got the original Mochi, then we've got a lot of action from AMD. Intel, HBM is a chiplet-based product that's available. Intel sort of, so there's a lot of chiplet activity. But what's interesting about all the chiplet activity is any multi-chiplet product typically comes from a single company and integrates products from a single company. And what we're trying to do is sort of say, can you build chiplet products by integrating chiplets from multiple companies, right? And the economics, again, are kind of interesting. This is from a paper by AMD, which I think is, I guess, the second CEO who writes papers at IEEE conferences. And the data on the left says, look, our die is so large, multi-core, where splitting it into 4 die is 30% cheaper. The data on the right is from yet another ex-IBMer. So one of the things I found in this, we're working on the chiplet stuff, is pretty much everybody worked at IBM at some point. All the packaging guys, all the microelectronics guys, everybody worked at IBM at some point in their life. And this one is from a gentleman in Montgomery, who did a rare assembly. I'm guessing a bunch of you may know him. But his basic point really is to somewhat to deal with the board aggregation model. And so what the chart does is it compares 3 options. It says I have a base product, and now I have a choice of 2 options. I can either integrate into build an integrated product through a multi-chiplet product, or I can build a shrunk product by combining multiple features into the next board and the next process node. And the basic point that the chart makes is that a integration gets you a lot of the benefits of a process node shrink at a fraction of the cost. That's the basic idea, that integration is a good start, as a good alternative to a process shrink and far less expensive, right? And I'll skip this for now, but one of the things we do as an open group is we have a lot of attendees, and every once in a while we poll them. And the interesting thing, actually there were 2 interesting. We did 2 surveys, and both of them were really interesting. So one survey is this that I have here, which is basically, everybody split on what the biggest problem is in chiplets. But everybody wants to somehow participate in developing the ecosystem, either as services or building some product for the chiplet market. Now, we did a separate survey, which I forgot to include in this, and it turns out when you want to build chiplets as products across multiple companies, you have to share data that you would normally not share. You have to share die physical data, and you have to share bump maps, and you have to share the Z dimension, you have to share what the thermal profile of your die is. And so we did a survey of your audience, of our audience saying, would you like to share this information? I was astonishing. Every engineer said no. Every product manager and business person said yes. It was a really lovely split. Every engineer in the audience said, no, wait, this information is too secret to share. And every business person said, well, of course we have to share it, and we're going to find a way to share this information. So what got us motivated was that when you look at a domain-specific accelerator, roughly 35 to 40%, or sometimes even 45%, of your die area goes to commodity logic. It doesn't go to differentiated logic. So that commodity logic can be network I/O, memory I/O, host I/O, internal memory, and network on a chip, whatever. But you have to implement that entire, all that logic. And typically the way companies try to manage their complexity and expertise is by buying off-the-shelf IP. And either in the form of hard IP for analog macros or soft IP for digital components, and putting them into their chip, right? And one option we're looking at is, what if you could buy these macros as chiplets instead of as chips? That was one, the disaggregation model. And then you start getting interesting economies of scale. Your SerDes can stay on a more mature process node because they're not going to really benefit from significant shrink. Your CPU processor cores are not going to be, if you have 8 or 16 cores, you can start using them across multiple die. So there's a bunch of interesting options in our mind. That's the basic, this is the kind of basic reference architecture we use. I waded through a whole bunch of papers, and almost all architectures have this basic thing in common, that they have about domain-specific logic, and they have a lot of general-purpose logic. And we started out with saying, let's target that general-purpose logic. So ultimately, we need to develop a stack between a networking stack to connect all our chiplets. And the networking stack is like any other network. It's got a file layer, and it's got to logically transport data. And the interesting thing I found was that there's always a holy war at the very bottom of the stack, and there's a holy war at the very top of the stack. And in the middle, there's like this great open room for compromise. So if you looked at our chip, originally we started out saying we want to target organic substrates, and then Nikhil guy said, well, if you can build a stack that accounts for interposers and bridges, we'll work with you. So then we said, okay. So our goal, we put that, and then what our goal is to define a stack that encompasses a whole bunch of multi-chip models, whether it's interposers or organic substrates, or whether it's whether it's the cache coherence mechanism is CXL or something else, right? Or CXL, OpenCAPI, C6, there's a whole bunch of options. But the point is to define a stack by which the chiplets can talk to one another. And there are a whole bunch of, so I'll come back to how the stack becomes relevant, but what we've done as a group is really work our way up the stack. We had a couple of papers that wanted to connect on stack options. That was on Thursday and Friday about 5-layer stack options. We have a group of people working on the link layer. How do these chiplets talk to one another, the link layer right now? But this is our basic goal, is to define this open stack. And what we want to do is create a marketplace of chiplets. And for that marketplace, we're targeting a very specific narrow slice of the stack. Something that works on organic substrates, low-cost interface between chiplets. And in the marketplace, there are two models. One is to support board aggregation, when you want to shrink a board in, or die disaggregation. But we want to support a very specific portion of the stack. So our ultimate goal is to create a marketplace of stack compliant chiplets, have people build chiplets for that marketplace, and enable people to assemble products from that marketplace. And to help them assemble products, so we essentially have 3 broad groups. We have a group interface standards that is trying to define that stack. Then the second thing we have a lot of reference designs, POC work, to show people how to assemble these, multi-chiplet products from that stack. And finally, the third thing that we're trying to figure out is we figure that the way you do business has to change. Like margin stacking, you have to somehow find a way to distribute product margin to the people providing individual chiplets. You have liability issues if your product is dependent on chiplet and chiplet gets EOL, how do you handle that? So a whole bunch of issues. And we have a group of people looking at saying how do you do business and how does workflow change with when you move to a chiplet-based development model. So these are 3 broad activities. Sorry, this is an eye chart, but this is actual. We have about 4 activities that, and I'll go into more detail if any of these look. I have more slides than these. So the rest of the talk is about boring you with mind-numbing detail of each of these things and whatever rocks your boat. But we basically have 4 things. One is we have like a fairly nice and detailed analysis of inter-chiplet files. So the actual mechanism, the file layer by which bits move from one chiplet to another. There's a whole bunch of competing options out there, and we put in a lot of effort into figuring out how to compare all of these in a way that all the vendors can agree is fair. And then we also as a group have a proposal for a new interchiplet file, because I'll come to why in there. That's the bunch of wires interface, the bowl is a bunch of wires. Then we have a fairly hefty group doing a prototyping work for multiple chiplets. Then we have a group looking at a very interesting idea of a chiplet design exchange. And the idea is that if you're going to create a chiplet marketplace, there need to be some ways in which you describe your chiplet physically. Some packaging guy told me the story of how the design team and the packaging team had a very different definition of the axis on which the chip was flipped. And so the packaging team flipped it this way and the design team flipped it this way. And so when they packaged the chips, the bumps didn't match the pins and the chip didn't work for a year until they figured out the die was perfectly good and it was the packaging that was broken. So our basic aim in life is to get everybody to agree on what 0, 0 is, whether it's the center of the die, in what order you go and define your bumps, how do you know, and then we have a couple of ideas on how do you describe the readiness of the chip, the standards to which it's tested. So we essentially, each one of these we're hoping will result in some kind of a spec or a standard. And I'll walk you through some of our activities. And an activity that's kicking off is how do we define the link and the network above it. That's another activity we have kicking off. And the others are sort of on our wish list. The business workflow keeps going, but the rest of the things you see, reference architectures. Our reference architecture really is for something like inferencing or video transcoding. If you do machine learning, you have a lot more I/O bandwidth between learning engines. So you need a very different reference architecture. So what I'm going to do in the rest, in the 10 minutes that I have, is just walk you through, and please, if you could tell me what you find interesting, I'll stop there, or I'll just keep zooming through. I'll walk you through the interconnect. So it turns out that there is this interesting war brewing on package, off die interconnect. And it basically boils down to two sort of broad camps. One group of people take an on-chip bus and move it off-chip. But you move 2,000 wires off the die. And if you're going to move 2,000 wires, you need an interposer, or you need a bridge, a silicon bridge, or some other technology. So Intel's AIB kind of falls into that bucket. And there are a bunch of people who do HBM-based interfaces, they fall into that bucket. The other group of people take an off-package serial bus and move it on package, and then your die-to-die interconnect is some kind of a SerDes. The advantage of the serial buses is that they're dead simple to design. The advantage of the SerDes is that they require very few wires, and so you can package them on an organic substrate. The catch is every SerDes that we've met seems to have tremendous design costs for each process node. And one of the goals that you're trying to achieve here is heterogeneous process node integration. You want to be able to combine die from multiple different process nodes. And so sort of the ideal interchiplet bus is something that's the DARPA has a huge project that's entirely dependent on large parallel buses because they depend on process nodes that go as far back as 180 nanometer or at least 90 nanometers and 180 nanometer. They've got all these defense processes and they can't do complex analog design. So we don't have to go quite that far. We think commercial products will stop at around 22 is our guess, although expert opinions tell me even that's too conservative. But ideally what we're looking for is a bus that's easy to design, can be routed on an organic substrate, like the way a SerDes bus can. So the answer in our minds is this idea of a bunch of wires. And literally, the bunch of wires is just the best name we could come up with, which is take a parallel bus, run each wire more quickly, do double data rate. So what you can do is, if you have a simple basic design, you can do 4 gigabits per wire. If you have terminated lanes and you've got more sophisticated design, you can do 16 gigabits per wire. And the idea is that you can also use the exact same wire for bidirectional transmit receive. You can now double the beachfront bandwidth. So the whole name of the game when you're doing these inter-chiplet connections is how much beachfront bandwidth do they occupy, how many wires do you have to route between die. And with this, we came to a very surprising conclusion with the. So it turns out that when you design SerDes, because you have a lot of digital logic, you have a lot of, you have FEC and you have more power, the actual area under the pin for each SerDes design is pretty substantial. So you end up having a pretty substantial footprint for a SerDes design. The actual number of wires you route between chiplets is far fewer. But on the whole, this design, this proposal is reasonably competitive with SerDes in terms of wire count. So you can do a terabit per second on 1 millimeter of beachfront bandwidth for the most advanced bus, which is enough to meet a lot of needs. So the idea here is that somehow we're trying to make this interface as open as we can. Can we define basic slices, bump maps that then get propagated? Then we are defining how these bumps talk to each other, how interfaces go up, etc. And then we're also trying to make this interface definition so that it works with bump spacing, whether you've got sort of very coarse bump spacing at 130 micron, or whether you have really fine bump spacing at 50 micron, or anywhere in between. But the idea is we want to propagate this interface. I think basic and fast can potentially be designed by even university teams. You can be supported as an open source implementation. The turbo implementation probably requires complex, good teams to design it. So that's our interface, and I'll come back to this in a bit. So our prototypes, we build a huge bunch of. Our aim in life is to build a huge bunch of prototypes. Currently, this is where we are. We're trying to build a test board with 3 accelerators, 3 chiplets. And the idea is that this board serves as a software development platform. And what we're going to do then is take those 3, and these boards today are based on existing die, 3 die, one from my company, Netronome, a 16-core RISC CPU from NXP, and a FPGA from Economies. What we've done is build a test board where anything that's a separate component has its own daughter card, basically. So we've got this base board, and so if you have your own accelerator, you can reuse this design, toss one of the components, and replace one of these 3 boards with your board, and you can create a package. So what we're trying to do is create this pretty nifty idea came from a guy at Cisco who's been helping us. And his idea was, why don't I give you guys a base board with 3 daughter cards? So if you want to use, what we're hoping is that this serves as a software development vehicle. It also tells us which is the most likely best case use case for a package part. So our goal for the package part is to have 4 40 gig I/O, and we're going to use fiber to the package from Stantec and put it into one package. And if you like this, we are happy to have you design. If you have your own custom accelerator card, a product, you can replace the FPGA, or you can replace a Netronome chip, or you can replace a RISC CPU, like with the PowerPC. If somebody has a PowerPC daughter card, and we can make a custom package. But the interesting thing about this is we're trying to do all this entirely in the open. And what you can see is, as usual, we're trying to raise money for this effort. So if you have some lying around, please give me a call. Right, so this is a test board platform architecture. We're targeting networking, machine learning, and storage as sort of broad use cases. It's got some storage hanging off it. It's got some, and the idea, what we're trying to do is, with 2 of these I/O, network I/O, we want to build a ring of accelerators. So you can share state across different cards. That's the basic intent. We think that we can, if you're on the Netronome part, we'll program it using data path using P4, and the RISC CPU will be programmed using a straightforward GCC compiler, and the Economies FPGA has its own tool chain. So this, we've gone through, I'll skip through this. So the nifty thing is if you've ever done an open project, getting started is incredibly painful, and then nobody wants to be responsible for the next guy's part. That's like turned out to be a real, so the neat thing about this design is each company gets to design their own pitchlet and push it on the baseboard. Every designer is like it's kind of like if you're familiar with OCP's OAM project, it's like a mini OAM, a mini OAM option. So then our last, I spoke about this Chiplet design exchange. There's a company called Zulu who is pretty active in our consortium. They've designed chiplet-based IoT products, and they have an internal specification we want to use as a starting point for this discussion. But the whole idea is like, how do you come up just with a standard way to describe the physicals of a chiplet? And then finally, the fabric. Right? Ultimately, we have to build a fabric that glues all this together. The one simple option for the fabric when you're doing board-to-package aggregation is to simply use PCIe on the inside. And the huge advantage, or I'll come to the OpenCAPI version the same, but the PCIe, if you have a board where you use PCIe on the outside, you just shrink it into a package and use PCIe as your transport protocol on the inside. All the software that ran on the board will run on the package. Boom. No porting issues. The only trick is you have to make PCIe run inside your package on these small, short SerDes. If you are doing die disaggregation, there's a case to be had for a new protocol. Just like AXI is on the inside of an ARM-based SoC, you need some kind of a new protocol, link layer protocol and routing protocol for die disaggregation. We as a group are trying to define that. If you're interested in joining us, please drop me a note, or I'll show you how to do this at the end. Right, so this pipe, so one of the interesting things about PCIe is that there is a standardized interface. I think this is what Paul and Brian and I discussed a couple of days ago. There's a standardized interface between the MAC and the PCS sublayer. So now if you can build an adapter from the pipe interface into your SerDes, any off-the-shelf PCIe controller will transport PCI over your short-reach file. So it's not unique to a bunch of wires, any of the files. And that's why if you look back at the stack, this was an idea from Can-Do. If you look back at the stack, you see that pipe adapter across all of these. And the idea is if you do that pipe adapter, then you have a very simple board-to-package aggregation model. As long as your short-reach file supports the pipe adapter, an off-the-shelf PCIe controller will work with your pipe adapter, and all the software that runs on the board will now port into your package. That's the thinking. So there seems to be a very clean design path if we're going to do board-to-package integration. And what we're hunting for, and I don't think we came to a conclusion, was that if we had a similar interface abstraction in the OpenCAPI world, then you could take an OpenCAPI board and look, assuming you could manage the thermals and which is a separate assumption. If you had the interface abstraction, then an OpenCAPI MAC layer would find a way to work with the short-reach SerDes, short-reach PHY, short-reach Bow interface, whatever your short-reach interface of choice is. Right? So we feel that if you have this interface abstraction, there's a very clean path for package to board integration and how to save power on the package to board integration. The other interesting use case is for die disaggregation, and so help me put these together. Thank you. And the whole idea here is, if you go back, one of the prime motivations for, if you go back to this reference architecture, it was interesting. We had a workshop at Intel, and we had a panel with designers from Cisco, AMD, oh, and East Silicon, Intel, and one other company, I'm trying to remember what, and Xilinx. And the interesting thing was, what part would you like to buy as a chiplet today? Was a simple question, right? And uniformly, everybody wanted a collection of SerDes, like quad SerDes, octal SerDes, or for long-range SerDes as a separate chiplet. And one of the things I think that OMI gives you is the ability to pull out memory as a separate chiplet. I think one of the interesting things that is there is you can use either internal memory as a separate chiplet or the interface to external memory. Basically, OMI creates a long reach PHY, a longer reach PHY than the traditional memory. And so if you can move that to a chiplet, then you can have one single chiplet which can be shared across multiple designs. So what we're speculating, and this is absolute speculation, is that if you had your CPU generating native OMI traffic of some kind, just like we ported PCI to a short reach interface, whether it's Bo or Candle's USR, so it was there. If you can port the OMI onto, let's say, a short reach interface like a bunch of wires, then you can sort of centralize all your off-chip accesses on a memory interface chiplet. So you can build like a quad PHY or an octal PHY. And then all that chiplet can be built in a more mature process node. It can share economies of scale. There's a bunch of interesting advantages because the basic theory we have is that the short reach SerDes, it's easier to move that across different process nodes, and the cost and complexity of moving that is much lower. So OMI just becomes a transport protocol by which you move memory references from point A to point B. So today, we're assuming this is our understanding, and then you can sort of see where you can move the memory as a separate chiplet. Now, Mr. Sutarcha here, who wants to take it to its logical extreme, says, well, once you're going to pull it out, you might as well just make it a module. The memory itself, you can package it onto. So use OMI as a transport protocol from the CPU to a memory chiplet. But now the memory chiplet is not a collection of PHYs, but it's the memory itself. So you could think of it as, I've got like, you probably say it better than I do. Would you like to take a shot at it? Or
no, which one?
The one on the right side.
I guess maybe the idea is, if we look at the cell phone today, a lot of high performance SoCs, like tablets, we have SoCs, and then with also LPDDR interfaces at the corner of the chip. Take a look at Apple iPhone chips, the Huawei chip. They all look the same. You have many PHYs for the LPDDR4 on corner chip, and then they have to use POP package. And in case of Apple, they have to use the CoWoS package from TSMC, not the cheapest packaging technology in flat. But they need that because they need performance and they need the density. What, on the other hand, instead of doing that, we separate the memory. Instead of putting on top of the processor, instead of using POP packaging, the memory could be a module. So companies like Samsung, Hynix, or Micron will be able to. They built, the job is to build the memory die, and they built this memory controller chip that we're going to see in the next 5 o'clock, 5:10. Microchip is going to disclose a memory control chip which has a series interface. Instead of that, there is a singular memory controller chip. The interface is not series, but this bunch of wire interface. And then now you have the processor and the memory module, but the difference will be that in the case of this chiplet, the memory will be stacked on top of this memory controller chiplet.
So
now you can put next to each other, then you don't need POP packaging, you don't need CoWoS packaging, you don't need expensive packaging technology. But we have to agree on that bunch of wire interface need to have, let's say, 8 gigabit in second instead of the standard gigabit. Not just that, you can also be like very dense, so you cannot do wire bonds technology and all the things.
So we think there's potential for using OMI as a memory transport protocol for memory disaggregation inside die. And you get a whole benefit of heterogeneous integration. And if there's a way to figure this out, I could use all the help, we as a group can use all the help we can get. There's a whole bunch of people. I just want to, we have a bunch of engineers working from companies that haven't endorsed this effort. So just because you see a name in there doesn't mean that the company has endorsed this effort. This is people who are volunteering their time. We've got a bunch of people from Cisco, Facebook, Economies. You can see it's NXP and Intel, a bunch of companies. I'd love to see more IBM names there at some point. That would be very nice too. How you can, whoa, this is a slide with the build. Who knew? All right. We have a wiki where we hold workshops once every 2-3 months. Mendy has been nice enough. Mendy and
I was about to say, where's the IBM name on that?
right there.
Okay.
Right there. Mendy's been nice enough to, Mendy and Anthony have been nice enough to host our next workshop. It's at IBM in Almaden on September 12th. But everybody's welcome. Please register. And we meet weekly on Fridays. You can find us on the calendar. We also, all the stuff we have, our past workshops, all the specs and slides, is all on this wiki. And I hope you can join us. Thank you for your time.